Good morning, everyone. Welcome to day 2 of our two-part training. Again, I am Angelu Pagaba of GPDP. As a continuation of yesterday's training, today we will be having the Advanced LNG course. But before we start, we would just like to again thank our US partners who made this training possible. CLDP of the US Department of Commerce, USAID Asia Gas Partnership, US Energy Association, and our funder, US Department of State. Also, just a few reminders. We will have the Q&A session after the presentation. So if you have any questions, please post it in the chat box. Alternatively, you may also opt to ask your question directly. So just press on the raise hand icon during the Q&A session. And lastly, we will be preparing certificates of attendance for the participants of today's training. So kindly make sure that you answer the attendance form so we will have your complete details. A link to the attendance form is posted in the chat box. Now, let's proceed with our presentation. We welcome once again our esteemed expert, Mr. Anthony Scaraggi. Mr. Scaraggi, you may begin your presentation.
Thank you very much. Once again, I'm very, very happy to be here. And hopefully we'll be able to share some lessons learned from the past from LNG projects. Let me open up the screen properly. Okay, so today's session is titled Advanced LNG, and the topics that we'll be covering are listed here. We'll have an overview of some basic components that we didn't already discuss yesterday. Yesterday we had pretty good, we dove pretty deeply into some of the specific components in LNG facilities. We'll talk about some of the design considerations, actual commissioning considerations, and a little bit about operations. Just to recap a little bit on the basics of LNG, I think would be helpful before we dive right into this particular lesson. Liquefied natural gas is nothing more than natural gas that has been purified a bit to remove some components that would otherwise cause problems in the systems that are used to turn it into a liquid. It's turned into a liquid at minus 260 degrees Fahrenheit. And it's stored at basically atmospheric pressure. It's a cryogenic liquid. It is non-toxic, non-corrosive. As a liquid, it's non-flammable. The gas that's liberated from LNG when you heat it up is natural gas, and its flammable range is between 5 to 15% in air. It's lighter than water. The vapors from natural gas are natural gas vapors are normally lighter than air, so they rise if released. But keeping in mind, LNG is a cryogenic liquid. When you first release the LNG, the initial vapors you get will be very cold, and those vapors will remain heavier than air until they're warmed up to about minus 160 degrees Fahrenheit. At that point, they'll be neutrally buoyant so any warmer than that, they'll raise. They'll dissipate into the atmosphere. Also a reminder, just like natural gas, liquefied natural gas is made up of several different components. And when we talk about the specific properties of LNG, we're really giving a number that's kind of like an average, because each of those different components within LNG can be in different concentrations, and those different concentrations lead to different total mixtures, and each of those total mixtures can have slightly different composition, slightly different properties than other compositions, causing LNG to have a range of properties. So once again, when you hear somebody talk about something like the temperature of LNG being minus 260 degrees, if you hear somebody else say minus 258 or so, neither is wrong. The actual properties are in a given range. So lastly, when we talk about LNG, it's generally stored as a cryogenic liquid at atmospheric pressure at its saturation, temperature, and pressure, which means while it's being stored, it's slowly boiling away inside its container. And it's maintained in a cold state purely through the insulating properties of the vessel that it's being contained in. So you can think of most LNG storage containers as a thermos, a big thermos bottle, and any heat that does penetrate that thermos bottle, just like if you have a hot drink in a thermos bottle, it eventually cools off. If you have a cold drink in a thermos bottle, it will eventually warm up. As you have your LNG in your big thermos bottle, as heat enters into that LNG, it causes a small amount of that LNG to turn back into a gas and be released as a gas. And in the industry, that's called boil-off gas. And as the LNG remains at its saturation temperature and pressure, boiling away slowly, that boiling effect is actually carries the heat out of the LNG. So the LNG remains at its saturation temperature and pressure while it's boiling away. Just like a pot of boiling water remains at 212 degrees Fahrenheit or 100 degrees Celsius while it's slowly boiling away, LNG remains at its saturation temperature, which, although once again is not an exact number and it does change over time, is about minus 260 degrees. So it boils at minus 260 degrees. So that's just a little review of some of the things that we talked about yesterday. And now we'll jump into the topics for today. This is an overview of the basic components in an LNG facility. So there's pumps, there's piping systems, there are recirculation systems. So LNG, as you know, is cold. The piping systems that it's in, if you don't have flow in those piping systems, over time, the heat penetrating into those piping systems will cause the LNG to warm up, cause vapors cause it to vaporize, and eventually you could actually warm up that piping. So there's the systems in LNG piping systems. Some of them have a continuous recirculation of LNG through those systems to maintain them in a cold state. Talked a little bit about the concept of boil off. That boil off has to be taken care of somehow. You can't leave it in your tanks, whether it's an on-land tank or whether it's a ship. You have to somehow handle that boil off. If you don't remove it from a closed system, you'll eventually pressurize the system, and LNG systems are not pressurized systems. So there are units that are called cold blowers that are generally used in LNG facilities, and all a cold blower is a compressor that removes the boil off, removes the vapor generated from the boiling LNG, pressurizes it a bit, and pushes it out of the tank into a piping system. There's equipment that's used to make sure that those vapors in that that are liberated from the LNG are maintained in a saturated state. So those vapors remain at just on the brink of becoming liquid, and those units are called desuperheaters. And you spray a little of the cold LNG into the warmer LNG vapors to cool the whole thing down and remove the extra sensible heat that the gas has accumulated. Compressors, many compressors, very big compressors in LNG facilities. We talked about that yesterday as a major component in the liquefaction process. And you use those. You also use compressors to take boil-off gas and bring it up in pressure to deliver it someplace else. So as I said earlier, LNG is at about atmospheric pressure, which is a very, very low pressure compared to typical pipeline pressures where gas would be delivered into. So if you wanted to take that boil-off gas and put it into a pipeline, you'd need a very large compressor to compress it up from, let's say 2 psi up into pipeline pressure, which could be 1440 psi. So very, very large compressors at LNG facilities even on the gas side, meaning on the cold side. There are also units called recondensers, which are is a piece of equipment that allows you another method of controlling boil off or processing boil off. Recondensers allow you to pressurize the gas to a slightly, not a slightly, depends on your outlet pressure, but to an intermediate pressure as opposed to going to full pipeline pressure. And that gas is basically reabsorbed by a liquid stream, by liquid natural gas that's being pumped to units that we called yesterday vaporizers that would be used to turn that LNG back into a gas for use in the pipeline system, right? So you can use a recondenser if you have continuous vaporization from the facility, or if you're continuously using the LNG in the facility, you can control boil off or help manage boil off using a recondenser. Also, fuel systems. You can use boil off as your own personal fuel in the facility. Every facility needs to have some sort of fuel that it's operated off of, and you can use your boil off to run your own on-site equipment. So LNG facilities are usually their own first customers. Continuing on basic components, LNG facilities are huge users of power, of electric power, and it's common to find on-site generation, gas turbines, the same kind of equipment that you'd find in power plants that are used throughout the world to generate their own electricity, to be able to power their own equipment. And once again, that fuel supply to that system would normally be LNG vapors. You have air separation equipment to provide on-site nitrogen. Nitrogen is used in LNG facilities for many different reasons. One reason that's used is for general maintenance purposes. Anytime you do some kind of maintenance on a system, you want to make that system safe, so that operators or mechanics or contractors who are working on that system are not working in an environment that's hazardous to them. And nitrogen is used to purge systems and piping of natural gas before work is done on those systems, so it can be done in a manner where the workers are not exposed to natural gas and possibly the hazards associated with that, normally being that natural gas is flammable. Also, when you put a system back into service, you generally purge, depending on the size of the system. But one of the normal considerations is whether or not you purge the air out of the piping or out of the components before you introduce natural gas back into those systems, so that you don't have a combustible mixture in the equipment or in the pipe while you're reintroducing natural gas into the system. And as I said before, you need fuel gas. Normally, LNG facilities are their own first customer. That said, if there's a pipeline nearby, it's very possible and not uncommon for LNG facilities to actually take gas from pipeline systems to use as fuel. And I said, if there's a pipeline nearby, well, normally there is a pipeline nearby. So it's just a matter of tapping into that pipeline and properly metering the gas and using it in your facility. Design considerations. When you're building an LNG plant, be sure that you've got professionally done hazard operations, hazard identification, process safety analyses, layered protection systems to protect the public, to protect the facility, to protect the equipment from any kind of mishap or human error that could possibly occur. So LNG facilities, just like any other plant, are facilities that have their own specific hazards. And just like any facility, if they're not operated properly or not designed properly, there could be safety concerns. And you eliminate those upfront in the beginning in your design by using these various processes. In the PSA and the hazard and the HAZOP, you do there's you can liken it to a what if analysis. If you have a valve, and what if that valve fails, what happens downstream, and then how do you protect the downstream equipment from that valve failure? And you methodically go through the whole plant, and you analyze each node within the plant, and determine what hazards exist based on what failure mechanisms could occur, and then you build in mitigation measures to address those. One of the ways you do that is with systems that are interlocks and permissives, meaning that you have areas in your plant where a particular valve might not open unless a particular temperature condition is met, or a particular pressure condition is met. So even if the operator tries to open a valve in a certain system, that valve will basically check itself and say, hey, wait a minute, should I really open? Are the conditions proper for me to open? And if those conditions aren't met, that valve will not open. That's just an example. When I use a valve, it could be any component within the LNG facility. Cause and effect diagrams are developed, and once again, that all comes right out of the HAZOPs and hazards. And basically, it's a way to a way to classify or categorize or identify all the possible conditions that could occur based on specific causes. Based on a cause occurring, what's the effect within the plant? So if I have a high temperature discharge on a vaporizer, what should happen? The effects might say that you would close an inlet, reduce the flow to the vaporizer, or shut down a vaporizer completely, depending on what has been decided by the HAZOP, and all the valves associated with whatever that effect would be are all listed within that cause and effect diagram. So you generally have a big grid structure that details what effects you get from what causes within a plant. Staying on design considerations, you have to think about where you're going to put this thing, right? You have an LNG plant that takes up a lot of real estate. If you're lucky enough to be in an area that has roads accessing the plant, that's great, but that's not always the case. You have to build your own roads. You have to be able to get equipment in on those roads. Vendors need to be nearby to be able to service equipment. Contractors need to be nearby to service equipment. If they're not, you need to have methods to get them into the facility. If you're remotely located, the actual selection of the site is, when you consider different sites, the elevation of the site is important. The seismic conditions in the region are important. All that stuff has to be evaluated. All is tied into your design of your facility, and all the mitigation steps that are required based on that your specific facility siting are also included in the design. Generally, the tanks are located in some sort of raised area, 10 to 30 meters above sea level. That alleviates flooding concerns, especially when you're a facility that accepts LNG or by ship or produces LNG and sends it out by ship. You're going to be near a waterway. So there's always flooding concerns in those situations that need to be considered in your design. And we talked about sheltering the facility, so that goes along with the flooding concerns. Okay, major consideration in LNG facilities is the whole fire protection system. LNG facilities, whether they're just natural gas, meaning whether they're just LNG facilities that do not make their own LNG, if they're a receiving terminal, or whether they're a facility that actually takes LNG takes natural gas and turns it into liquefied natural gas, meaning an export style facility or a liquefaction facility, have many components that are for, and a fire study done, taking the full design of the plant into consideration,
Mama, sabi
determining
niya, ano,
and determining where those different components of a fire detection system should be located based on the design of the facility, right? So one particular standard, Nfpa 59A, has detailed requirements, and this is a section from 59A, has detailed requirements on what needs to be done for that fire study. This is NFPA 59A is a standard that's been adopted by many different municipalities and countries. Well-known standard, well-developed standard, that's used for the design, construction, operation, maintenance of LNG facilities, and this is some of the language in that standard around the requirements of a hazard analysis or fire protection study. Critical part of deciding where you put your components that do things like detect natural gas leaks, detect the concentrations of natural gas in a facility, detect any form of ignition that might exist in the facility, smoke detectors, detectors that sense the change in temperatures, the rate of change in temperatures, elements that where elements should be placed that can detect leaks by let's say a rapid decrease in temperature. Many different components are associated with the fire protection systems within the facility, and those are all the detection systems. On top of that, there is actually suppression systems. So you have fire suppression equipment, the dry chemical extinguishing equipment that could be used to suppress an LNG fire, and actually eliminate the fire. You have water systems which are not used to extinguish LNG fires. They make a fire hazard worse in LNG, but you use water systems to shield equipment from heat. You use water systems to control vapors. So when you have an LNG leak, as I said earlier, the LNG vapors are heavier than air until they're warmed up. You can actually use water to actually heat those vapors up and to control where those vapors travel and keep them away from ignition sources. So there are many considerations that go into the designing a plant on the fire protection side, and it's critical. It's a critical part of being sure that you can operate a facility that's got the hazards all under control. One thing that you'll always hear in the LNG industry is that you should avoid flanges, right, on piping systems, and that's excellent advice. Flanges can leak. LNG is very cold. When you first introduce that cold liquid into a piping system, you do it in a very controlled manner, because it will make the pipes contract. The pipes will move as they begin to cool down. And normally, as you can see here on a flange, you've got many bolts. Normally, the bolts will contract at a different rate than the actual steel. So you'll get a situation where you won't have a complete seal on a flange during cool down. And when that happens, you can actually get LNG leaks from the flanges. As time goes on, if you monitor that, generally, once the bolts and the flanges all cool down together, the leak will stop. The flange will seal up on itself. You can also retorque the bolts if that doesn't occur. All that being said, so flanges are a source of a leak in an LNG facility, but they're also critical in being able to do maintenance in a facility. Without strategic flanges in strategic areas, repair and replacement of equipment could take an awfully long time, especially equipment that you have to, regularly maintain. You can imagine if you have a system that has no flanges, the alternative is to have a completely welded system. And in order to remove a component from that system, you'd have to cut that component. You'd have cut that component out. You have to cut the piping. You'd have to then take the component out, do whatever work you needed to do on that component, and then put it back into the system. You have to re-weld that piping together. All that welding work on piping systems requires you to then recertify the piping through pressure tests or some other means. To do, when you initially do the removal work and you do the cutting of the pipe, you have to make sure that you properly purge the systems to remove any combustible mixtures. So it becomes a very, very, very time-consuming job to do maintenance work. So you have to balance that against assess that against the likelihood of leaks in your piping systems if you're using flanges, and determine which flanges should strategically be in place and not be eliminated. To be able to do maintenance on these systems, and to be able to do it safely, there's a very, very common method called providing a double block and bleed. So equipment that would be worked on needs to be isolated from the LNG source. So you could close a valve and isolate LNG moving into that piece of equipment, but you don't want to just rely on that valve for safety purposes. Any kind of leakage by that valve could cause could be a hazard to somebody working on equipment downstream of that valve. So you then have a way to vent that pipe downstream of that valve, and then you close another valve on the other side of that vent. So you have two valves stopping the flow of LNG, and in between those valves you have a vent, so that if any LNG passes the first valve, it doesn't pressurize the second valve. It actually is removed from the system. And monitoring a double block and bleed, or the bleed on a double block and bleed, lets you know if your valving system is actually operating properly to isolate the source of LNG from the equipment that's being worked on. and placing these double block and bleeds, I went back a slide, sorry about that. Placing these double block and bleeds in proper areas so that you can do maintenance without taking without having to take large pieces of equipment out of service, allows you to maintain a facility safely, quickly, and effectively. Excuse me. Control systems that are in place in your facility need to be tested to be sure they're actually operating at their as they should. And you should build provisions into the facility to be able to test those control systems while the plant is online without affecting the safety or reliability of the operations. You can do that with redundant control systems, redundant control architecture. You can do that by having remote workstations that are used exclusively for testing purposes and that do not affect the actual operation of the facility. You can also do certain inline testing where you can take a component out of service while keeping the rest of the facility in service, and you maximize the uptime on that facility. The idea of when you build one of these facilities, so to give you an idea, a liquefaction export facility can cost, easily cost $10 billion. That's a huge amount of money. Any downtime is basically a loss of money to the facility. So the idea is to be able to maximize your runtime, and you do that by building these redundant systems in and having systems in place like double block and bleeds, so that you can perform maintenance while as with the minimum downtime and in a safe manner. Installation, general considerations. When you're installing components in an LNG plant, remembering that LNG is minus 260 degrees, any moisture in that LNG will freeze on contact with it. So you really want to keep things clean and dry. You want to purge components before you actually introduce LNG into them, purging them to reduce the moisture in those components, to dry them out, so that you don't have any residual moisture that would freeze out and possibly harm equipment. An interesting consideration in LNG facilities. So when you go into LNG facilities, you'll see valves with these very, very long stems like this. These valves should be installed in a vertical manner, as in this picture here, and not installed in a horizontal manner, as in this picture here. So picture this, and why do you want to do this, right? Picture this, you've got LNG minus 260 degrees in this valve, and then LNG rises in this valve handle, right? Inside this valve handle, the LNG begins to vaporize and forms a vapor pocket. And that vapor pocket actually seals the valve stem in the valve. That's the design of a cryogenic valve, the basic function, the basic way a cryogenic valve works. If the valve is installed horizontally, you don't have the vertical space for the gas pocket to form and actually cause the seal. You'll always have liquid in this line, and you'll give yourself a point for leaks. So that's a design consideration in LNG facilities, and not just LNG facilities, any cryogenic facility. Excuse me. Commissioning is it's a huge part of building a facility, putting a facility into service. The things you have to consider before commissioning or for commissioning are things like, your nitrogen purge. How are you going to purge the equipment to remove moisture, to remove oxygen from the systems, to eliminate, the hazard of possibly having a combustible mixture during startup. You can do a nitrogen purge. You can then purge with the product itself, meaning purge with a refrigerant or natural gas vapors. These are all considerations in commissioning. How are you going to cool down the piping? We talked briefly about how when you introduce LNG into piping that has not been cooled down yet, how that piping shrinks, how that piping contracts. The whole piping system moves. So that cool down of that piping, initially cool down of that piping, is very, very critical. You don't want to impart any stresses on that piping that would damage it prior to it actually being used, right? Also, when you have an LNG tank, you have to cool that tank down, and that's a very, very methodical job to cool down a very, very large storage tank. So these are all the considerations that need to be completely thought out ahead of time before commissioning. Things like then once you're ready to go, what's the sequence of actually commissioning? Which components do I introduce LNG into first? Do I do it from the tank backwards? Do I use a piece of equipment in the middle of the tank, in the middle of the liquefaction system, let's say, and start introducing cold elements into that, and start producing LNG, and start running LNG to the tanks and using it to cool the tanks down, the piping down? It's all different considerations in commissioning. When you're considering commissioning, you have to come up with some kind of performance measures to make sure the facility actually operates in the way it was intended to operate, and meets the requirements of the design, right? So there's performance measurements. You need to have a way to take those performance measurements. You need to have your performance targets, and you need to run your facility to be able to measure those performance measures during commissioning. and things don't always go right. So in your procedures, it's absolutely critical you consider, plausible conditions, plausible abnormalities that might occur during commissioning, and have plans in place to be able to mitigate those. Okay. Commissioning preparations. Train. You got to train people. You can train people on simulators. You can train people in the procedures. You just train to be sure that any challenge that comes up can be addressed in a safe manner. Calculate some of the things you need to do for commissioning. You're going to need things like nitrogen, right, to do purging if you're doing it in that manner. Well, you better know how much you need, and you better make sure you have it on site. So you make your calculations and you order the stuff that you need. Calculate the amount of LNG that you need for cool down and for heal in a tank. Sometimes you might want to cool a system down with a cargo of LNG, as opposed to cooling it down with your own LNG that you start with in production that you produce. So you might want to calculate how much LNG you have to purchase to do an effective cool down that way, an alternative to producing your own LNG and using it during cool down. You have a significant amount of venting normally when you're doing commissioning of an LNG plant. And in some jurisdictions, there are limits, or there are permits required to be obtained from the authorities to be able to legally do that venting. So make sure that you've got any permits that you need. Calculate the amount that you expect to vent to be able to convey that properly in the permitting process, and be sure that you've got those in place. Before you do any commissioning, you ensure that you've got mechanical completion of the facility, meaning that it's mechanically ready to have natural gas introduced into it. And you definitely have to be sure that all the safety devices are in place before you actually do commissioning. So these are the steps, some of the steps. There are many, many more, but some of the basic steps that you would prepare for when you're preparing for commissioning. Very first thing you do in commissioning, as you commission, is you bring all the safety systems online. So before you introduce gas into the facility, you make sure that your shutdown systems are all working, tested, and proven. You prove that all the control systems operate as they're supposed to operate. The valves open and close as they should. And that's what this means here, stroke all valves. And you commission the fire protection system, which is the system that was installed based on the analysis of your facility that was done very, very early on, to determine where all the gas detectors and smoke detectors and such, and whatever items are necessary for your facility. Those are all installed, and that whole system is commissioned. When you provide your own fuel gas, generally it has to be heated up, because as we know, LNG is cold. And when you take LNG gases, or any gas, and it's a pressurized gas, and you're reducing in pressure very, very quickly, you get a cooling effect. And so that gas needs to be warmed up before it can be used as a fuel. So you need to provide heating for the fuel gas. And, as a little joke down here, sometimes you need to provide fuel for providing fuel to heat the fuel gas, right? So you have to figure out how you're going to do that. How are you going to have fuel to heat your fuel gas before you have fuel gas, right? You set commissioning targets, critical. Make sure that you've done your analysis, and you have your go points. We're going to purge the system, and these are examples here. This is not something that you take away and use as definitive points for your system. through analysis, you determine what your targets should be. So, for example, in nitrogen purges, this is typical. Make sure you've reduced the oxygen content in the system to less than 9.5%. If you're drying out pipes with the nitrogen purge, you want your dew point to be less than 40 degrees Celsius. And if when you're drawing your tanks out, you want your tanks to be at least minus 30 degrees Celsius before you can feel comfortable introducing LNG into the tanks. And I'm not sure if people understand what that means. The colder the dew point, the less moisture there is in that gas. So by reducing your dew point to a very, very low temperature, what you're actually saying is make sure that the gas in the piping in the tanks is dry before you introduce the cold LNG. Once again, because cold LNG would freeze out, would cause any moisture to freeze out and can block flow and cause damage in equipment. A purge may require using 6 times the volume of the actual system to get a good purge. And once again, that's just an example. There are models that you can use to determine in your system what the actual amount of purge gas would be required to achieve your targets. Once again, setting your targets, knowing your limits, generally 2 days to cool down process piping. So to take that piping from atmospheric conditions, let's say it's 90 degrees out, before, and you're going to introduce minus 260 degree Fahrenheit LNG into that system. It's going to take about 2 days to initially cool down the piping. You cool it down very, very slowly. So you're going to introduce those stresses associated with the piping system contracting, and possibly, if you don't do it slow enough, you risk damaging the piping systems. Once you have it cooled down, you immediately introduce the liquid and the LNG liquid into the system. And in areas where you start circulation to maintain those piping systems cold. So this is typical for, let's say, a line from the facility to the dock, where you would either receive LNG and pump it into the tanks, or you would take LNG from the tanks and deliver it to a ship for export. That piping system would be a piping system that would fall into this category, where initial cool down would take about 2 days, give or take, it depends on a lot of other things, how long the pipe is and such. But as an average, 2 days. And then you immediately introduce LNG into that system once it's properly cooled down, and you continuously circulate through that LNG through that unloading line to maintain it at its cold temperature. For cooling down a tank, 1.5 days about. Once again, these are not hard and fast rules. These are ideas of what these targets look like, and you want to build what's called a heel in the tank, meaning a small amount of liquid in the tank that will keep the whole tank cold. And typical range for that is you build about 5 inches of liquid into that tank in about 12 hours. What that means is you're introducing liquid into the tank very, very slowly. That liquid is cold. It's being introduced into a warm tank, and initially that LNG just vaporizes, right? And as the LNG vaporizes, it cools off the tank. As it cools off the tank, you'll get to a point where you'll start actually having LNG remain as a liquid. Once that happens, the liquid level will build up slowly as the tank continues to cool down. So this target here is a target of about 5 inches of liquid in a tank after 12 hours of cool down. That's what we have today for some of the aspects of piping systems and commissioning LNG facilities, and what the considerations are that go into design and what really needs to be done to operate things safely and efficiently, and how the industry handles those things. Open for any questions.
All right. Thank you very much, Mr. Skaraji, for yet another detailed presentation. So we will now be having our Q&A. We will be reading the questions posted in the chat box. And we also open the floor to participants who want to ask questions directly to Mr. Skaraji. Just please press the raise hand icon. So let's go first to the questions in our chat box. We have a question from Mr. Joseph Gerard Reyes of GPDP. He asked, how long days, months, or years will be the training duration for personnel who will perform the commissioning runs?
So commissioning is always performed by veterans. So they will have been trained in the industry for quite a while, generally, years and years and years. They're very experienced people. Commissioning teams also include people who will be operating the plant. So those people will actually be getting their training during the commissioning process. It's hard to give you an answer, a direct answer to that question, because it will have been people who are very, very experienced and have generally have lived through multiple commissioning processes and plants, or who will have been people who have worked their whole careers possibly in LNG facilities. Commissioning is a very, very critical process, and it's an area where you work the bugs out in a facility. So you really want the most experienced people involved with commissioning. I hope that answered your question.
All right, thank you. Let's move on to the next question from Suzanne Logan. The presentation, which was excellent, seems to be from the perspective of the project sponsor, such as commissioning preparations. Can you talk about the typical role for the regulator during all these projects? Perhaps reviewing or approving designs, observing commissioning tests, or requiring testing certificates, etc. Also, how many of these design considerations are totally internal to the project or set by international standards, or need to be spelled out by the regulator?
Can you repeat that? I'm kidding. So regulators have a huge part in the whole design of an LNG facility, and it does depend on the jurisdiction that you're in. But from a U.S. perspective, I'll give you that, which is the perspective I have the best. From a U.S. perspective, every aspect of an LNG facility's design is reviewed by the regulator before a shovel is even put in the ground, before a piece of equipment is even purchased, and that those discussions dive into details, into design details, from safety, which is obvious, right? From safety concerns through environmental concerns, through reliability concerns, all the way through. And there are schedules that are set for reporting of the progress of a project, and for inspections by the regulator during the project, the installation of the facilities. So it's the design, it's the installation. All through the installation, there are inspections and reports that are required, and then even during the design, even during the installation, the regulator can still add additional, I'll say, demands on the project or on the facility based on what they've seen happen in the facility, how they've seen things progress. And then the whole commissioning plan will be reviewed by the regulators to be sure, so that they're sure that all the safety concerns are being addressed during the startup. The training that's required of the people who will be operating the plant, all the training records, the training methods, the training programs are all reviewed by the regulators prior to them actually being able to operate the facility or introduce gas into the facility. And these are all the reviews are done by or according to many different standards, international standards, some US in the United States, some US standards, but there's a huge amount of coordination between the regulator and between the developer, constructor, EPC contractor. That's all. It's totally interconnected. I hope I answered that question.
All right. So for our next question is from Miss Cynthia Murray. Other than the flammable vapor dispersion and thermal radiation from hazards associated with LNG, what other hazards should be evaluated in the siting analysis for an LNG plant?
So there are many hazards. You can imagine, any process plant has many hazards. When you consider the hazards that were just described there are major hazards for consideration: thermal radiation and vapor dispersion. But those are only hazards associated with, well, not only, but mostly associated with the LNG, right? There are other components in there are other substances in an LNG plant that each have their own hazards that need to be considered. So, for example, if you're building a liquefaction facility, you'll have many components that are used to actually as refrigerants to actually used to liquefy the natural gas. And those components, maybe things like propane, isobutane, isopentane, liquid nitrogen, and all of those have their own hazards associated with them. Some other components may be toxic. Some components may be just as asphyxiants, just like natural LNG can be if it's released and the heavy vapors, right along the air and right along the ground and fill low spaces. So you have hazards of thermal radiation, of fire. You can have hazard considerations around stored refrigerants, such as possible levee conditions that could occur. You have hazards associated with the facility, with the siting itself. So you have geophysical hazards. You could be in a high seismic area. You could be in an area subject to tsunamis. Those kind of hazards also need to be considered in the design of the facility and how it will be able to withstand those kind of situations without adding to the hazard from them. So you don't want an earthquake to cause, which is already a huge hazard, to impact an LNG facility and have it multiply the hazard in the region or for the people on the plant. Toxic considerations, like I said before, some components within LNG facilities, can be toxic. So you need to, LNG itself is not toxic. So you need to have sensors in the proper places where you could possibly have a leak of something toxic, right? So if you got like an ammonia situation in your facility, if you're using ammonia for something, that's a toxic substance, and you could have a release of ammonia. When you talk about the hazard from thermal radiation and from vapor dispersion, those hazards are generally based on very large failure scenarios, right? The likelihood of that happening is very, very low. The likelihood of something smaller happening, something less catastrophic happening, is higher, and those considerations need to be evaluated right up front in your initial design of your facility, so that you put things in place to mitigate any kind of hazard from that type of unwanted scenario that might occur.
Thank you.
All right. So for our next question, we also have Mr. Don Honor B. Jacob. Do NFPA 59A and EN 1473 cover all components of LNG storage and regasification import terminal, from construction to installation to assembly to testing to commissioning to operation and maintenance?
So the EN standard, the European standard is so the answer is yes, with a bunch of qualifiers on that, right? The European standard is very different than the 59A standard. 59A standard is a prescriptive standard, and within it, it does have it covers every aspect of an LNG facility, from design to construction to commissioning, to initial commissioning, meaning initial startup, to taking systems out of service, to decommissioning, to operator training, to maintenance, levels of maintenance. All that stuff is in there in a prescriptive manner. The European standard, which I am not as familiar with as 59A, so I'm going to talk a lot more generally about that, is a risk-based standard where you have much less prescriptive requirements and much more risk-based analysis requirements. So you don't you propose a process or a system or a design to the regulators based on the risk analysis you've done for your system, and how you've mitigated that risk down to certain levels that are considered acceptable for those, for the region, for the municipality, whatever's been agreed to by the jurisdiction having authority. So the answer is yes, definitely yes for 59A. Most likely it covers all those things in the European standard, but they would be covered in a very different manner than the 59A standard would cover them.
All right. So for the next question, the question from Miss Eva of PPA PMO Palawan is more of a question for the Philippine DOE. So I think we will answer it through email instead. So let's move on to the next question from Mr. Cerces Fernandez. Can you give examples of US policies on standards such as CFRs or state regulations we can use as reference?
Yeah, so within the United States, the regulation, the CFR for LNG is 49 CFR 193, and that is the driving regulation. NFPA 59A is referenced by the 549 CFR 193 in certain very specific areas, but the ruling code is NFPA. Is 49 CFR 193. That's primary code for LNG facilities in general. the shore side stuff or the water side components of LNG facilities are covered by in the U.S. by the Coast Guard, and those have their own CFR. It's 33 CFR 127, and there are specific requirements within that, just like in 49 CFR 193, where there are requirements for everything from design to operation. It goes the same for 33 CFR 127, which has all aspects of the LNG systems from the marine side.
All right. So we have a question again from Mr. Don Jacob. In commissioning of LNG pipeline and LNG storage tank, do you first introduce cold natural gas, say negative 140 degrees Celsius, or just very small amount of LNG, say negative 162 degrees Celsius, pumped very slowly and let it stay that way for say 1.5 to 2 days?
So the answer to that is, to both of those questions, is yes. I know that sounds a little strange, but you will start a cool down with cold LNG gases first, and then introduce liquefied natural gas after that. They're generally inside the tanks. Part of the design includes a header system, which is used to spray LNG into the tank to start the cool down. You spray that LNG into the tank, in the beginning, it immediately vaporizes. So you have cold LNG vapors that are cooling down the tank originally. As the tank gets colder and colder, those vapors, that LNG doesn't vaporize and becomes LNG droplets, and those droplets of LNG, so the actual LNG liquid begins to accumulate in the tank and cause the cool down. That said, that's very general. There are very specific procedures that need to be developed to cool down an LNG tank safely and without damaging the tank. And manufacturers so tank design manufacturers to tank design manufacturers will all have their own very specific procedures on how to cool down tanks. But generally, it's through that spray header that's in all designs that you initiate the cool down. And when you start, the LNG is warmed very rapidly and becomes a cold vapor before its liquid is actually introduced.
Okay. Mr. Joey D. Balankit from DOE OIMB would like to know the key drivers that govern in the design and cost of an LNG receiving facility.
So say that again, I'm sorry, the key drivers
that govern in the design and cost of an LNG receiving facility.
LNG receiving facility. So the key drivers are you have to have a customer, right? You have to have an area that requires the fuel, that requires the LNG. So in a receiving terminal, that customer can be a pipeline that's located nearby that has limited supplies from other areas. That customer could be a small local distribution system that's being built or exists and is being converted, let's say, to natural gas. So the real driver is the need for the fuel. Usually, I mean, there can be a project where, build it and they will come kind of thing, but that's very unlikely and not normally done, right? The cost considerations for an LNG facility, an LNG receiving terminal, are So one other thing, I'm sorry, about customers. So you have a receiving terminal. I skipped a whole possibility there. You could actually ship the LNG out of the facility in trucks to various other customers that other people who could use LNG, who could become customers in the region. So you can actually physically truck the LNG to other satellite tanks where customers can use them, or to other areas where they have constraints in their piping systems and they need LNG during certain times of the year for peak shaving type applications. So that's the driver for deciding whether or not you should try to build a receiving terminal. The cost considerations, major cost in a receiving terminal are the tanks and is the dock, right? Two of the major components. So when you select your site, you need to have a deep water port. And if you can have a deep water port in an area where you've got minimal currents, minimal tides, you make your design much easier. You make it much more cost effective. One design consideration around the dock is that if you have rapid currents, you can have lots of scouring, and you need to do a lot of dredging over time to keep your dock area accessible, by ship. So you'd want to minimize that by being able to locate, if it exists, if a spot exists, being able to locate in an area where you have a deep water port, low currents, low variation. On the plant side, it gets more difficult. It's an optimization exercise. How frequently you can get ships, how frequently you want to get ships, what your supply contracts look like, all drives, and your customer profile, your customer take profile. What all those things together drive how big your tank really needs to be able to constantly meet your customer demand, to meet your required output. And so you have to balance that. So you want, from an operability, from a reliability perspective, you want the biggest tank you can possibly have. You want to be able to accept a ship anytime you want and not worry if you have not received a ship for a period of time for whatever purpose, whether it's weather purposes or whether there's some kind of strife in the company in the country that's your supplier. So you'd really want to have as much LNG on site as you can. But tanks are expensive, right? They're a very expensive part of of a receiving terminal. So you have to balance the risks associated with the ability to receive and bring LNG into the facility with the levels of reliability that you need in your plant. So those are the drivers. In my opinion, those are the major drivers in an LNG receiving terminal.
Thank you, sir.
You're welcome.
All right. So we also have a question from Mr. Asterio J.R. Gallardo from PPA. With regards to the comparison of construction of a coal power plant with imported coal as raw materials to provide energy to the Philippines, is there a possibility that Philippines can embark importation of LNG to provide power? If yes, between the two sources, which do you think is much cost efficient for our country?
So I think the question is, and correct me if I'm wrong, the question is, should we generate power from coal or should we generate power from LNG? Right? Is that the question? There are many components that go into that consideration, and generally you wind up on the side where where natural gas is the better solution, right? And that's because if you take into account the whole kind of chain associated with coal production and the emissions from coal and the effects on the environment and the effects on particulate matter that's released during burning coal, the effects of that on health, general health of the population. When you take all that stuff into account and you compare it against the same exact categories or the same exact effects that natural gas can have, the natural gas ones are lower. And when all the calculations I've seen say that when you consider the full, when you don't just say it costs this much to build a coal plant and coal costs this much money. So if I operate, it's going to cost me, I'm making up a number now. This is totally made up. It's going to cost me, 50% of what it would cost me to build a natural gas plant and use natural gas to develop to generate energy. When you do a consideration like that and you disregard all the other aspects associated with using coal as opposed to using natural gas, you wind up with an analysis that seems to makes it seem like that coal is the right solution. But when you consider the total cost associated, both to society and to the environment, natural gas generally wins out. Almost always wins out. I've not seen one set of calculations that says it doesn't, but I'll leave that open. It's possible, I guess, right? Just in my experience, I haven't seen that. So natural gas, so coal is a very, very complex fuel. Natural gas is a very, very simple fuel. When you burn a complex fuel like that, you wind up with a lot more byproducts that you need to do something with. You need to process. You need to somehow remove them from the environment. Natural gas being the basically methane, the smallest, simplest hydrocarbon, burns much more cleanly, much less effect on the environment. That said, they're both still fossil fuels, no doubt about it, right? So natural gas is not like a solar or wind or renewable in that sense, right? It's definitely not. It's still a fossil fuel. So you don't get the benefits, the environmental benefits you get from pure renewables, but you get way better than you do from other fossil fuels. So the considerations are that whole value chain, and when you do that whole value chain, all the analyses I've seen have said that that natural gas is a winner.
All right. So in the interest of time, we can accommodate only 2 more questions. So we will have Engineer Marshall Batong of PFP and Director Rino Abad of DOE OIMP. Actually, Engineer Marshall Batong is the first one to send his question, but it is directed in a private message. So let's address it first. So the question from Engineer Marshall Batong is, NFPA 59A is for LNG facility. Can we use NFPA 101 life and safety code for ancillary of the LNG facility?
You absolutely can. There's no reason you can't. It's all depends on your agreements with your regulator, the authority having jurisdiction. I don't remember off the top of my head, but within the NFPA 59A, there are many other standards referenced. I'm not sure if that one is directly referenced in there. All that being said, the 59A standard covers all the safety, life safety aspects as well. And in areas where it doesn't, it will certainly reference another standard. So yeah, so the answer is I would say is yes, but how it's applied becomes the critical part of that.
Okay. And for our last question from Director Rino Abad. How do you choose which standard to apply when you have NFPA 59A for USA, 49 CFR Part 193 for USA, EN 1473 in Europe, and JGA rules for plants and storage?
So how do you choose which the question is, how do you choose which standard, which regulation? And that is really the conversation between you and your regulator to make that decision. So there's usually some authority that has jurisdiction over those decisions in whatever region you're in or whatever country you're in, or whatever municipality you're in some cases, and that's a conversation with the regulator to come up with those. In some areas, where regulators might not be as up to date on the different standards that are available out there. There are projects throughout the world that were built and developed using all of those standards. And it's very common. When I was the last LNG facility I was in, it was very common to get visitors from other jurisdictions to our facility to see how the regulations worked in real life, while they were deciding, what they would use, what they would hold the developers to for the projects that they were developing. That said, 59A is NFPA 59A is a standard that's regularly used throughout the world. In the countries that do not make it regulation, actually many times refer to it and reference certain portions of it, and sometimes 59A is used to augment the regulation that's required by the regulator.
Okay. I think the question is being asked by the regulator himself.
So the regulator, as a regulator, you get to pick, right? You get to decide what the standard, what the regulation, what the code should be that's used. But you don't have to make that decision in the vacuum. You can require to be educated by the projects, by the developers, on the differences between all the standards and all the regulations that are available out there. And you can reach out to agencies like Nfpa for a complete I'm going to say description or understanding of the philosophy behind their standard. I'm sure U.S. regulators would be happy to entertain conversations with you and share their ideas as to why they believe their standard is the one that should be applied, universally. So yeah, it's a decision that the regulator makes, but does not have to make in a vacuum.
All right. Thank you very much once again, Mr. Scaraji. And thank you all for your questions. So for those whose questions have not been answered, we will be taking note of them and we will send you our expert's response after the training. All right. So to close today's training, may we now call on Assistant Director Rodela Romero of the Department of Energy, Oil Industry Management Bureau to deliver her remarks.
Thank you very much, Angelou. Am I clear?
Yes,
Malinaw
ma'am.
ba? Mukhang kinakareer ko ng pagde-deliver ng closing remarks. Congrats to Rhea. Hati tayo sa prize mo. Okay. To our sponsors, cum organizers, the GPDP2 and the U.S. Department of State and the Commercial Law Development Program teams, USAID Asia Gas Partnership, U.S. Energy Association and GTI, and to our energetic resource speaker, Mr. Anthony Iscaraji. I hope I pronounce it right, sir. My DOE family, headed now by Director Rino Abad, participants and guests, ladies and gentlemen, good morning. The current crisis we are experiencing, I am referring to the coronavirus health issue, is not a stumbling block for us to continue our interest, to learn, and to work hard, especially for an initiative that would make a difference to the landscape of the energy situation in the Philippines. And another crisis, this time energy crisis, might happen when operation of Malampaya gas field project will close for good in the near future unless we find an alternative energy resource such as LNG. So we need to fast track everything from legislative agenda. Fortunately, we have one in Senate, SB 2203, regulatory framework, the PDNGR, which serves as the Bible of the downstream natural gas industry stakeholders, the soon development and promulgation or adoption of international technical standards with the help of this team and our interagency monitoring team for HSSE, and of course, capacity building activities such as this training, among others. All of these initiatives will unlock the untapped potential of natural gas, especially LNG, in order to achieve greater Philippine energy stability, sustainability, and savings. Your topics on basic and advanced LNG for this two-day training would definitely increase your knowledge on the components, design, and installation to commissioning of the technologies that can be used for different application and markets. I am sure that everyone appreciated every topic in this training module, and I hope that our capacity building program is a continuing one so we can develop a pool of experts on LNG. Again, on behalf of the Department of Energy, through the leadership of Secretary Alfonso Cusi, and our very own bureau here, the Oil Industry Management Bureau with Director Rino Abad, with our Natural Gas Management Division headed by Ma'am Laura, thank you very much for all your supports and looking forward for a positive outlook for LNG industry in the nearest term. Marami pong salamat, stay safe, and mabuhay tayong lahat. Good morning. Thank you very much, Angelou.
All right. Thank you very much, Assistant Director Romero, for that inspiring message. So before we conclude the training, may we please request everyone to open your cameras for a quick group photo. Let's show your beautiful faces. All right, everyone ready? In 3, 2, 1, smile. Again, 3, 2, 1, smile. 3, 2, 1, smile. And 3, 2, 1, smile. All right. Thank you very much. We would like to inform you that we have posted the link to a short evaluation regarding our two-part training. So we hope you can take time to answer it. We would greatly appreciate your feedback. So that concludes our training. We once again thank our resource speaker, Mr. Anthony Scaraji, for all his time and effort in putting the presentations together. Also, thank you to Mr. Cousin Leo, Ms. Sarah Blanford, and to all other U.S. colleagues and representatives who helped us organize the training and for also joining us today. We likewise thank all the agencies and government units for your active participation, and we look forward for having you in GPDP's future activities. Have a nice afternoon and evening, everyone. Stay safe.
Thank you.
Thank you very
Thank
much for
you,
having me.
everyone. Bye.
Thank you.
Thank you very much.
Thank you very much.
Thank you.
Thank you. Thank you.
Thank you.